Hello and welcome everyone. Thank you for coming. My name is Won-Soo Kim. I'm a postdoc researcher in Human-Robot Interface and Physical Interaction Lab at IIT. Today I'm going to present about the mobile and reconfigurable collaborative robot framework, which is called MOCA-MAN. Before moving ahead to the main topics, the question is that why the collaborative robots are important in industry. There are reasons here. The first reason is that the working forces in industry are getting aged. And the second reason is that they lost a huge amount of money due to the work-related musculoskeletal disorder. And the third is that the production line demands more flexibility. So to address that kind of the issues, there are an example of the cobots and the exoskeleton that such a collaborative robots are successfully introduced and integrated to take on the physical demanding task instead of the human workers, such as the repetitive task or load carrying task and so on. So that such technology will be able to mitigate the workloads of the workers. Although the effectiveness of the collaborative robot is obvious to help the human in industry, however, still there lack of the functionality to move towards the more future industry in flexible and in reconfigurable aspects. Regarding the cobot, there is still may use it in the fixed platform, and it takes mostly in the repeated task as similar as the old industrial robots. So which means that it is hard to object into the flexible working environment. On the other hand, the exoskeleton can be caused another burden to the wearers to change their configuration due to the wearing the equipment. So it's caused another fatigue at the wearers. So to address this kind of issues, we propose a new collaborative framework is unify the system that can be configured quickly between the cobots and the supernumerary limbs to be able to cover the large range of the industrial task requirements. It will lead the reduced equipment waiting and setup time through the exploiting the concept of the modularity. To present this topic, the first consideration is the flexibility. It can be represented by the mobile module that can be able to work in autonomous local manipulations. Essentially, we have been developed such a kind of the system is called the MOCA, the Mobile Collaborative Robot Assistant. The second consideration is the reconfigurability. So we consider the simple human-robot interface module that will be integrated in such a mobile manipulator. Then it turns into the human integrated platform to do some conjoint actions. It's working like as an exoskeleton. So the design of the MOCA-Admittance interface are represented here. This side will be connected to the human wearer side, and this side to the robot end effector side. For the agile configuration, the magnetic clamp works under the magnetic force threshold, whether it providing the strong connection when it clamped or releasing easily for the safety reason. So when it clamped, the human intention or the interaction forces are able to transmit it to the robot end effector for using in the conjoint action control. And the opposite case, the conjoint action will be terminated automatically. The overall control framework is composed like this. There are two main modes for the autonomous and the conjoint mode as working like as a supernumerary limb. And it will be distinguished by the switch sensor from the admittance interface, whether it clamped or not. To control the MOCA under the torque-based control, we construct the whole body dynamic model includes the mobile platform and the manipulator. As I mentioned earlier, the MOCA has been developed for the agile mobility. It is composed of the Robotnik mobile platform. The top of there, it is placed the Franca and the PCIe soft end for the grasping purpose. The whole body motion is controlled through the whole body impedance controller as well as the joint compliant control in the projected nerve space. The desired impedance parameter and compliance and the damping in the Cartesian space can be regulated on the targeted task. So for more details, you can find the related paper which was presented in the ICRA2020. Moreover, we extended this whole body impedance control idea with the weighted Jacobian method. Thanks to this method, we are able to handle the prioritized motions either in the mobile platform or on the manipulator while controlling the whole body motion. In this video shows that when the higher weighted are used in the locomotion, then most of the actions are exploited in the mobile platform by the manipulator. In the same targeted control, on the other hand, the weighted on the manipulator side, the manipulator has more prioritized actions than the mobile platform to reach the same target. So this works also will be presented in another session by the colleagues. So when the admittance interface is clamped, so the human intend to work with the MOCA, so the conjoined mode are activated in these situations. The target admittance action is to minimize the interaction forces to follow the human's motion. So the admittance controller is takes to generate the desired motion as the input of the whole body impedance controller by using the measured force from the force torque sensor, whereas in the admittance interface. To switch the mode and adjust the control parameter, the framework including the human gesture detection techniques through the Mayo armband. Before clamping the interface, the double tap gesture will call the MOCA. The MOCA will approach you at the targeted position that the motion is controlled based on the autonomous mode planner, including the self-navigation. And the fist gesture is engaged with the soft hand control to grasp the object or release it. When the soft hand is closed, it's pretend that the external object is holding on the hand, so then the stiffness parameters of the impedance controller is automatically set to a higher value. Then the MOCA is able to compensate the weight or the external forces at the end effector. And the last gesture is wave motion is employing to switch the prioritized motion between on the mobile platform on the manipulator during the task when it needs. So to validate our approach, the experimental setup are presented here. They will simulate the typical industrial task as carrying the object too far away. Through the double tap gesture, the MOCA start move towards the subject, and then the subject clamped interface. Then the conjoined action is started. Now it's working as the supernumerary limb of the human. After few steps of the locomotions, the subject needs to grasp the object with the precise control. So the mode is changed into the manipulation mode. Then the subject is able to handle it easily to grasp it. To move to the final position in the far distance, the mode is changed again to the locomotion mode, and then to move towards to finish the task. And the task are clearly to move it. The subject is trying to finish the task, and it can be easily release the interface by the users, and then the conjoined action is terminated. The result shows that the promising effectiveness, the first and the second row presented the position of the Franca and the Robotnik, and then change their prioritized motion through the gesture recognition. The major motions are switched between the manipulation and the locomotion. In the meantime, whereas the overall interaction forces where the carrying of the 3 kilograms objects are evaluated. It means that the entire control framework can physically support the subject not to against the human's motion, and the detachment forces of the magnetic clamp interface is measured when it was released. It was around 39 newtons. The value were consistent with the safety considerations we took into account when designing the magnetic interface. To validate more details of what the effectiveness of the physical support, we performed a separate experiment to measure the muscle activity while performing the drilling task. We compared the muscle activities on the with and without the support from the MOCA-MAN. As you can see in this plot, the overall effort among the subject decreases significantly during the support phasing. The value is around the 57 decrement ratio. So to conclude that we present a novel collaborative framework that incorporates the advantages of the collaborative robots and the supernumerary limbs. The framework aims at the high flexibility and the reconfigurability. This was achieved by the integrating an admittance interface into the mobile manipulator as known as the MOCA. So we expected that MOCA-MAN provides more solid evidence on the coherent reduction on the effort of the human partners in the realistic human-level collaboration task. Thank you for watching our works. You can visit to our website or the related project website.